In this video, we're going to continue talking about how equilibrium can be disrupted by a stress and shift to reestablish equilibrium. Our learning goals for this video are going to deal specifically with changes in pressure and how a change in pressure might alter an equilibrium system. We're going to be given a chemical reaction and use Le Chatelier's principle to predict whether a change in pressure will favor the forward or the reverse reaction of a chemical or physical system at equilibrium. We will also try and determine whether or not we think a change in pressure will lead to an increase or a decrease in concentration of reactants or products, which we can do once we've decided which reaction equilibrium will favor. You should already have watched a video that I've made about how concentration and changing concentration of reactants and products can impact equilibrium. And there's also a video that I've already made that talks about what equilibrium means. So make sure you've checked those videos out too. Let's get started talking about pressure. There are a couple of ways to change the pressure that gas is exerting in a space. Remember, pressure is simply measuring the force of collisions of gas particles on the walls of their container. One way to influence the pressure of a system is to change the temperature. When you learn about gas laws, we will talk about this again. We're not going to adjust the temperature because that can have other impacts on the equilibrium system. But let's think about another way that we could commonly change the pressure of a system, and that is by decreasing the volume. Notice how the pressure changed. Now that makes sense. Pressure just means collisions that gases are having with the walls of their container. If you decrease the volume, you are therefore decreasing the amount of space the particles have to move and increasing the number of collisions. The opposite happens when you make the volume bigger. The pressure decreases because you are lessening the number of collisions the particles are having with the wall and with each other because they have more space to move in. So for our purposes, when we say that we are increasing or decreasing pressure for a reaction, I'd like you to visualize just changing the amount of space that the gases have to take up. That's an easy way to think about increasing the pressure by making the space smaller, decreasing the pressure by making the space bigger. The next relevant factor to pressure I want us to think about is how the number of gas particles in a space will impact pressure if we don't change the volume. So let's say we're leaving the box the same size, but we're going to increase how many gas particles are in the box. Let's think about what that might do to the pressure. So our pressure is 4.7 atmospheres. When I pump in some more gas particles, it increases to 9.7 atmospheres. So increasing the number of particles in a space increases the pressure because it increases the number of collisions the gas particles are having. Conversely, decreasing the number of gas particles decreases the pressure, decreases how many collisions the gas particles are having. It is kind of intuitive. More particles, more collisions, less particles, fewer collisions. Let's quickly recap some of the terms that we've used to talk about equilibrium. When a reversible chemical system is at equilibrium, what we are saying, if we have reactants A becoming products B, that double arrow means the forward and the reverse reaction are both occurring at the same rate. That reaction is said to be at equilibrium. That chemical system is at equilibrium. The rate of the forward reaction is the same as the rate of the reverse reaction. Systems need to be closed for equilibrium to be established. The forward reaction and the reverse reaction are occurring at the same speed when a system is at equilibrium. In other words, A is becoming B, reactants are becoming products at the same rate that B is turning back into A, that products are turning back into reactants. And the concentration of A and the concentration of B remain constant. This does not mean that there is necessarily the same amount of A as there is of B. There's not necessarily the same concentration or the same amount of reactants as products at equilibrium, just that the rate of the two reactions are the same, and the concentrations of both reactants and products are constant or unchanging overall. And then to review Le Chatelier's principle, simply states that when a chemical system that is at equilibrium is disturbed by a stress, the system will respond in order to relieve the stress and return to equilibrium. The stress that we're talking about in this video is a change in pressure. If the forward reaction ends up occurring at a faster rate after the change, we say that the forward reaction is being favored by this change, and there is a shift to the right to reestablish equilibrium. It's the opposite if the reverse reaction ends up occurring at a faster rate due to the change. We would say that the reverse reaction is being favored and the reaction system is shifting to the left to reestablish equilibrium. So now that we've got some of those basic terms fully established, let's look at an example, and we're going to, of course, organize our thoughts into a table here. Now, this example shows a balanced chemical equation. It's the synthesis of ammonia gas. So 2N2 gas plus 3H2 gas reacts to form 2NH3 gas. At equilibrium, the reaction is also occurring in reverse. Notice, and this is really important, because we are looking at a system in equilibrium, it is important to notice which side has more particles of gas. So in other words, I'm not counting individual atoms, but I'm counting particles of gas on the reactant side, particles of gas on the product side. I see 1, 2, 3, 4, 5 particles on the reactant side and only 1, 2 particles on the product side. I could also get that by adding the coefficients. 5 on the reactant side, 2 on the product side. It really matters when you have a question that is asking you what the effect of a change in pressure will be on an equilibrium system to know which side of the reaction has more moles of gas. In this example, the reactant side has more moles of gas. We'll do an example where the product side has more moles after this. So let's think about what the effect of increasing pressure would be on this reaction. We need to think about which reaction that stress increasing pressure would favor. So let's visualize, because remember, at equilibrium, there are both products and reactants all together in a big mush, and all that we know, this is a static picture that's not moving, right? But if we picture all these gas particles are moving around, and for every moment that some N2 and H2 particles are reacting to form NH3, there are also some NH3 particles that are breaking apart to form H2 and N2. If we were to decrease the pressure, and in this case, I'm going to do that by showing that the volume is being decreased. So I'm going to increase the pressure. If I've increased the pressure, notice there's now less space for all of the gas particles to move around. This means more collisions are going to be likely. This will have a greater effect on the side of the reaction that has more gas particles because they will be more affected by an increase in pressure. They will be more affected by the fact that they can collide more because there are more particles. So watch this. There's now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total particles in this chamber. Now, let's imagine a reaction occurs. Do you see what I did there? I'll go back. A reaction occurs. 2 N2 particles and 3 H2 particles react to form 2 NH3 particles. Now, there are 1, 2, 3, 4, 5, 6, 7, 8 total particles in this reaction chamber. So there are now fewer particles in the reaction chamber because more collisions were likely to force the particles together, and the side of the reaction that had more gas particles was more affected. So equilibrium shifts to favor fewer gas particles in total. Another way to think about this, that is kind of a shortcut some people like to use, is the idea that, okay, if I'm increasing the pressure in total, a system will shift to reverse a change. So if pressure has been increased because the volume has decreased, the system can decrease its internal pressure by just reducing the total number of particles. The same number of atoms are on the screen in front of us. They're just rearranged, but the number of particles has decreased from 11 to 8. And when I say particles, I mean bonded together units. So as I increase the pressure, equilibrium shifted to favor fewer gas particles. In this case, if the reactant side has more moles of gas, increasing the pressure will favor creating more product, decreasing the number of gas particles by creating more product. The forward reaction in this case is creating more product. This will decrease the concentration of reactants because reactant gets used up faster if the forward reaction is happening at a faster rate, and it will increase the concentration of the products at equilibrium because the products will be made faster if the forward reaction is faster. Let's think about the opposite scenario. So we're still working with the same reaction, but let's imagine now that we decrease the pressure in the system instead of increasing it. So I'm going to show a decrease in pressure by showing an increase in volume. So let's say we widen the space of the container for these gas particles. Now there will be fewer collisions because there is more space in the container. So I've increased the volume, which decreases the pressure. This will lead to fewer collisions between all of the particles. That will have, again, a bigger effect on the side of the reaction that requires more collisions to occur. So the reactant side is now not going to be able to have its particles collide as much, and the forward reaction will be occurring at a slower rate than before. This means that the reverse reaction is going to end up being favored, and we will end up getting some more reactant particles back. Equilibrium will shift to favor the production of more gas particles. Again, another way to think about it is if decreasing the pressure was the result of the change, the system can increase the pressure again by favoring the creation of more gas particles, because more gas particles means more collisions. Just kind of two ways to think about it. So decreasing the pressure in this case is going to forward the reverse reaction, but it's just because the reverse reaction is going to make more gas particles. So decreasing the pressure is going to favor increasing the number of gas particles. In this case, it's the reverse reaction. This will increase the number of reactant particles, which get made faster in the reverse reaction, and it will decrease the number of product particles, which get used up faster in the reverse reaction. You might be wondering what would happen if we had a reaction that was the opposite. So let's look at our second example here. 2SO3 reacts to form 2SO2 plus O2. There are 2 gas particles on the reactant side and 3 gas particles on the product side. So in this case, the product side has more moles of gas. We will essentially see the opposite pattern here. Increasing the pressure in this case is still going to favor decreasing the number of gas particles, but in this case, that means the reverse reaction. So the reverse reaction will be favored to reestablish equilibrium because the reverse reaction is the reaction that will decrease the number of gas particles in the system. If the pressure is decreased, the forward reaction in this case will be favored because the product side has more moles of gas, and if the equilibrium system is going to increase the number of gas particles, it needs to forward making products, so the forward reaction. So when we're thinking about pressure and gas, we want to make sure we are figuring out which side of the reaction, reactants or products, has more moles of gas, and then use that information to think about whether increasing the pressure or decreasing the pressure will shift the reaction toward the products or the reactants. It really just depends on whether or not you're favoring making more gas particles if the pressure has been decreased, or making fewer gas particles if the pressure has been increased. Let's check back in on our learning goals. Hopefully you feel comfortable predicting which way equilibrium will shift, or which reaction a shift in equilibrium will favor, forward or reverse, as a result of a change in pressure. Remember, it's all about figuring out which side of the reaction has more gas particles in it. Our final video on equilibrium, we'll be looking at how changing temperature impacts equilibrium. So keep an eye out for that video to help us finish up one of the more difficult concepts in chemistry. Nice job today.